Okay, let's get started. So please, the homework for Wednesday has been up and continues to have things added to it, so I hope you check that out and you got started over the weekend. And then I'm going to post another web work. After today's lecture, I'll post another web work. That'll be due like Wednesday at 5. So you got lots to do. Make sure you're on top of it. Don't wait till 11 o'clock Tuesday night. Okay, so I just wanted to show you a couple. We're talking about parametric functions and how this kind of, by making ordered pairs a function of some other parameter, you get a whole class, a whole world of functions that we would never have thought of to be functions before, right? So this is not a function. Y is not a function of x, but this is this function where x is this function of t and y is this function of t. Okay? So another one here. Just some fun ones in here. Okay, that's a relatively non-complex parametric function. That's a pretty crazy graph, right? But this is t plus sine 2t is x. Y is t plus sine 3t. So in terms of like modeling curves in the real world, things that we wouldn't have thought of as functions before, parametric function could do it. That's the idea. Let's see if there's one more here. Ooh, cool. All right, so, and again, it's not super complicated, right? And these all have to do with sine and cosine, but that, that's even just sine and cosine is a very small class of functions, right? We got all kinds of functions. So polynomials, exponential functions, logarithmic functions can all be part of x and y. And so in terms of what's for Calc 3, this, like the sums and series is less important for Calc 3, but parametric functions is extremely important in Calc 3. Like it's throughout Calc 3, okay? All right, so I want you to, can you sketch this function? X is sine pi over 2t. Y is cosine pi over 2t. Sketch this one. Remember how we did this, right? Remember strategy we used to do this. We were doing the other way, though. I was giving you a curve, and I was asking you to find the function. Now here's the function. Can you sketch the curve? So I'll write it the way we're... Okay, so you should ask yourself, what does x do? What is the x coordinate going to do as t goes from, say, 0 to 1? What's the x-coordinate going to do? So you can make a table, like we did. What's the x-coordinate going to do as t goes from 0 to 1? Anybody? Yeah. 0 to 1, right? X is going to go from 0 to 1, because that's what sine of 0 to sine of pi over 2. That'll go from 0 to 1. So x will go from 0 to 1. And y will do what? As t goes to 0 to 1. 1 to 0. So y will start at 1, x will start at 0, and then we'll end up at 1, 0, right? X will go from 0 to 1, y goes from 1 down to 0. Straight line? Sine and cosine has to do with what? But the definition of sine and cosine is coordinates on what? Circle, right? A unit circle, right? So when you have sine and cosine representing x and y, you should immediately think unit circle, right? That's what the definition of sine and cosine are. Sine is the y coordinate on the unit circle. X is the cosine is the x coordinate. Here they're switched, and that's okay. But it's still gonna have the same kind of, idea. So something like this. In fact, I'm going to show it make it? No. It was nice. Okay, so as we go from 0 to 1, here's what happens. Here's what we get. All right, and then as t goes from 1 to 2, x-coordinate will go from 1 back to 0, and cosine will go. Yeah, and if you need to sketch the graphs, too, you could sketch the graphs separately of sine and cosine if that helps you. But as t goes from 1 to 2, we'll end up down there. And then as t goes from 2 to 3, x is going to go from 0 to negative 1, cosine, negative 1 to 0. And then finally, as t goes from 3 to 4, sine, negative 1 to 0. That's the x-coordinate, y-coordinate, 0 to 1. How many got it before I started talking about it? Okay, good, at least almost half. All right, good. And the rest of you were close. So, what circle is that? So this is a real basic circle. So can we write, do we know that equation as x and y? What is that equation as x and y? X squared plus? And what's that? So these are the same set of points, right? So x equals sine pi over 2t, and y equals cosine pi over 2t, and x squared plus y squared equals 1 gives us the same set of points. But this has something different than this. What's the characteristic of the parametric function that just the equation doesn't have? Okay, it doesn't have t, and then what is the effect of having t? Look, here's t, down here. So what does the parametric function have that just the equation x squared plus y squared equals 1 does not have? You're looking at it. Yeah, what are you going to say? You're
I was thinking that the parametric function has x and y as dependent variables.
right.
T,
Okay.
Whereas x and y, whereas the original circle equation is not.
Okay, so yeah, so one difference is he's saying this is a function. X and y are dependent, t is independent. This isn't a function, it's just an equation of x and y, how they relate together. Okay, but what am I showing in the animation that shows, so okay, so there's that animation. Let's do this. Watch. So now if I graph x squared plus y squared equals 1, x squared plus y squared equals 1 is in this lovely yellow-green here, right? And here's the blue, or the dark one, is the parametric version. There's a big difference here, Daniel.
With the equation, you are showing all points simultaneously.
Right.
Satisfy it, whereas with the parametric, you can show each individual point at a time.
Okay.
It's an accumulation function.
Could be accumulation. So as t increases, this graph has what? It has a way that the points are swept out. So I think that's what he's getting at. Yeah, go ahead. Okay, yeah, so that goes back to the fact that this is a function and this is not. So if this is a function, it has rate of change. That's good, yep. So with a function, you have rate of change. You could think of it as accumulation, whereas this is just kind of like you just get all the points at once, right? But there's one more subtlety to this, and that is that with x and y as a function of t, you get the curve has direction. There's a way in which the points are generated as t increases. So what is the direction of this curve? This way. What do we say? Clockwise. So the parametric function, this particular parametric function generates the points in a clockwise manner as t increases. Whereas x squared plus y squared equals 1, there's no direction associated with it. It's just all the points. So that's another feature of parametric functions that, say, just equations don't have. All right? They have direction. So the direction of this is, it's counterclockwise, and starting at, where does it start? 0, 1. When? T equals 0, right? So we can talk about the direction of a parametric curve. Okay, so if these give the exact same points, then somehow they're mathematically equivalent. How is it that these are mathematically equivalent? Who remembers their trig? What relationship do we have between sine and cosine? Jennifer, remember?
Yeah, sine squared x plus cosine squared.
Right. So if I wrote down sine squared of pi over 2t plus cosine squared of pi over 2t, that would equal what? 1, that's called a Pythagorean identity. But what is sine squared of pi over 2t? What is that? It's x squared. And what is cosine squared? It's y squared. Lo and behold. So they're the same, right? So they're the same set of points, right? And that mathematically shows how they're the same set of points. Use the Pythagorean identity, sine squared plus cosine squared equals 1. Well, then this equation just falls right out. X squared plus y squared equals 1. But again, the big difference is that the parametric function has direction associated with how the points are generated, whereas the equation does not. But mathematically, the same set of points. All right, so let's look at this. All right, how about this one? Okay, so notice this is a little bit different. Now we got 3 times cosine of pi t, 2 times sine of pi t. But you guys are becoming more skilled at this, so can you sketch this without technology? Sketch this without technology. See if you can do it.
So would you recommend like doing the graphs separately first? And then putting it all together?
Well, so yeah, it's not just the endpoint. So you say if you're going to do from 0 to 1, which is okay, what does sine do as this goes from 0 to pi? What does sine do?
Okay.
If you need the graph, that's okay.
Right.
But what does sine do? It starts at 0, and it does what?
Starts at 0 and then it goes to 1, right?
1, and then when it gets to pi,
It's to pi, which is 0 again.
back to 0. So it,
But then when you multiply by 2, it goes from
good. Yeah, right.
0 to 2, back to 0.
Right. 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 Yep. Okay, so where does this start at t equals 0? He wants 3, 0. Does it start at 3, 0? Okay, I got 1 nod, got 2 nods. Starts at 3, 0. And as t increases, so you could say t equals 0 to 1, but you're going to get a lot more going on, right? Now that it's pi t instead of pi over 2t. So maybe another strategy here would be let t go from 0 to a half, right? So you can break it down a little bit more. But if you can do t equals 0 to pi, but you got to keep track of everything happening. Sorry, t going from 0 to 1. But you got lots to keep track of in there, okay? So as t goes from 0 to, say, 1/2, right? As t goes from 0 to 1/2, what does x do and what does y do? X goes from x What does x do as t goes from 0 to a half? 3 to 0, good. And what does y do? 0 to 2. Can you imagine that? Or can you sketch it? Like that. So again, you can say t equals 0 to 1, but then you've got like, there's lots going on because x is going to go from 3 to 0, and then what? To -3. It does all that stuff as t goes from 0 to 1, which is okay as long as you can keep track of it. And then what does y do as t goes from 0 to 1? 0 up to 2 and back down to 0. Are you tracking with me? Is this making sense? It's kind of quiet out there. Okay, so then so that's why I recommend maybe let's do 1/2 instead. So as we go from 1/2 to 1 now, x is going to do what? Go from 0 to -3 and
From 2 to 0.
right. And then we keep going like that. And what do we get?
Kind of like the oval or ellipse.
Okay, so an oval is a shape. An ellipse is actually a mathematical set of points. So do we know for sure if it's an ellipse? Well, let's prove it. We can prove it mathematically if we can, just like we saw in the last example, if we can write that as an equation of x and y that we know is an ellipse, right? We can write that as an equation of x and y that we're certain is an ellipse. And so what can we use for that? How did we start last time? What? Cosine squared,
Plus sine is 5t squared.
right? Equals? Is that a true statement?
No.
Cosine squared plus sine squared doesn't equal 1?
Oh, it is.
Can I put 3 cosine? Can I put a 3 inside there and a 2 inside there? Then will it be true? It won't be true anymore, right? It's got to be cosine squared plus sine squared equals 1, and your arguments have to be the same. The angle argument has to be the same. So this is a true statement. How can we use this then to eliminate t and get it all in x and y? What does cosine pi over t equal? What does cosine pi over t equal?
So that'd be, in the first one, be x over 3.
Doesn't that equal x over 3? So I can rewrite this as
X over 3 squared.
x over 3. And what does sine equal?
Y over 2.
Y over 2. Have I written another true statement?
Yes.
Absolutely, because in this example, cosine of pi over t is x over 3. Right? Solve for cosine pi over t. It's x divided by 3. Sine of pi over t, y divided by 2. So therefore, if this is cosine and this is sine, then cosine squared plus sine squared equals 1. All right, so then I got x squared over 9 plus y squared over 4 equals 1. Is it an ellipse? That's our equation of ellipse, right? It's that ellipse, right? It has an x radius, or what's called the directrix. In the x direction, the radius is 3, and we see that as 9 in the denominator here, 3 squared. And then the y directrix, or radius in the y direction, is 2. So we see y squared over 2 squared, or 4, equals 1. All right, so now I'm going to give you the equation of ellipse, and I want you to write it parametrically. Any questions on this example? Here we go. 16x squared plus y squared over 9 equals 1. So can you write a parametric function that gets that same set of points, right? Can you write a parametric function that gets that same set of points? Okay, let's see how we did. Kyle, how'd this go? I can't see your, all I can see is your laptop. I can't see your face. There he is. You got halfway. Tell me what you did.
Well, I started to try to set up the y equals 8 lengths, so you did the t.
Okay.
I don't know how to do it, so
And then what'd you do after that?
I was trying to talk to him so I get a better idea how to do it, so I'm still confused.
Okay. How about Thomas back there? Okay. Raise your hand. Get help. You got both TAs wandering around here. So let's see. Yeah.
I got x equal 1 plus cosine.
All right. So never a final answer. Give me the process. Give me process. There's stuff to do here. So yeah. Okay. So what'd you do first?
X equal 1 plus cosine.
You just wrote that down? That's the first thing you did?
Oh,
That you just looked at that equation and wrote down what you're telling me? That's what you did? If you did, that's fantastic. But I couldn't do that.
I just get that.
You guessed. Okay. It was a good, really good guess. All right. How about over here? Ramiro, did you make any progress? Okay. Yeah. Riddick, go for it.
You gotta take the square out.
Okay.
So it'd be like 4x minus
Okay.
plus y over 3
Okay. Making progress here. Then what?
And then I got from that, I set it equal to like, so 4x equals something sine of t.
So you said 4x equals sine of t?
Yeah.
Okay.
And then I solve for x.
Okay.
So x equals sine t divided by 4. I was confused whether if it would be sine t or cosine t.
Okay, that's a good question. We'll get to that in a second. But let's just see if this works. Okay. See, and then what about this?
What was that?
Then what did you do after that?
Oh, and then, oh yeah, it should be pi t.
What's that?
It should be pi t, right?
Okay, pi t. Does it have to be pi t? Well, it's because all the other examples had pi t, so it must be pi t, right? Does this work? Yeah, right. That's the problem. Does this work? Is there anything he's done that's incorrect so far? Okay, let's keep going. What would we do next?
And then you put y over 3
Yep,
cosine t
yep. So y equals?
over y equals 30 cosine t.
All right, does it work? Is this the same set of points as that? Have we done anything? So from here we went to this. If 4x was sine t and y over 3 was cosine t, would that be consistent with this relationship right here? If 4x was sine t and y over 3 was cosine t, would this still be true? Sure. Sine squared plus cosine squared equals 1. So we have x equals sine t over 4, y equals 3 cosine t. So now if we were to sketch this, then we would want our t values to, it wouldn't be helpful to do t going from 0 to 1 and 1 to 2. Instead, we want t going from 0 to pi over 2, right? And then pi over 2 to pi. Right? So having those coefficients of pi over 2 just made it so that to sketch it, to be helpful, we would vary t from, say, 0 to 1 or 0 to a half. But if you just had t's in there, then you can vary your t accordingly. So now vary t to go 0 to pi over 2, and t from pi over 2 to pi. Okay? So if you have pi's here or pi over 2's here, that's perfectly fine. It's still okay. It's just what? It's just gonna generate the points kind of at a different rate as t varies, right? But it's gonna be the same points. Okay, so what ellipse is this? Let's predict what ellipse this is. What's our kind of our x radius here? What's our x radius? What's the x radius? Like 1/4, right? And then the y radius is 3. So we're predicting what? Like x radius 1/2 or 1/4, you said? And y radius of 3. So maybe we're predicting something like this. Ellipse, really tall, skinny ellipse like this. So we know that's what it is according to the equation. So let's just make sure that our parametric function does that same thing. So I'm going to put the parametric function in here. xy equals, this is the one we came up with. 1/4 sine t and 3 cosine t. So will we get, is that what we thought? Looking at that original equation, we said the x radius was 1/4 and the y radius was 3. And when I put that parametric function in that we got as a mathematical equivalent to the given equation, we get it, okay? So what are the features of this here? What are the features of this? This one starts at what and goes which way? When t equals 0, this starts at what point? You want 0, 3. Agree with that? Yeah, so you just put in t equals 0. And then does it generate the points clockwise or counterclockwise? How do you know? How can you tell if it generates the points clockwise or counterclockwise by looking at that? Okay, what about our strategy, right? Let t go from what? Let t go from 0 to pi over 2 and see how this varies, right? See how the x and y ordered pairs vary as you put in, say, t going from 0 to pi over 2 and then from pi over 2 to pi. So where does this go? As t goes from 0 to pi over 2, x goes from what to what? Zero to 1/4. Our x is going to go from 0 to 1/4, and our y is going to go from 3 to 0. So that will tell us clockwise or counterclockwise. Do you see that? So as t goes from 0 to pi over 2, x goes from 0 to 1/4, y goes from 3 to 0. Why am I doing 0 to pi over 2 now? Well, because my function is just t, right? And with just t, I want to choose those ranges of t strategically to help me, right? We know that 0 to pi over 2 is like 1/4 of the cycle. If you have pi over 2 in there, then you want t's to go from 0 to 1, etc., right? So you can choose how the t range is and choose it to make your life the easiest for how x and y will change. Okay, so this is going to start here and go clockwise. Okay, let me show you another thing here. So at pi over, so this is t equals pi over 2 right here. This point. What's changing there? Is x changing or is y changing as t changes at pi over 2? Does x change or y change? Or both? Or is x changing or y changing right there at pi over 2 as t increases? Is x changing at that instant, at that moment right there at pi over 2? Does x change? It's like a maximum value of x, right? What about y? Is y changing? Definitely changing, right? Y is decreasing. So let's look at the rate of change of y. So if y equals 3 cosine t, what is dy dt? What's dy dt? Negative 3 sine t. And at pi over 2, what's the value of that? So what does the rate of change tell us? The rate of change tells us how y is changing with respect to t. At pi over 2, dy dt equals? Negative 3, right? What does that tell us? If dy dt is negative 3, what does that tell us about how points are being generated here? Failure to connect. If a derivative is negative, what does it tell you about the quantity? Decreasing, right? So how does that agree with what we're seeing at t equals pi over 2, that the derivative of y with respect to t is negative? It's showing what? It's showing the direction of the curve, right? So we talked about that parametric functions have direction to the curve. Well, the derivatives can reinforce that, can show how that's true. At t equals pi over 2, y is decreasing, right? If we're going clockwise, y is decreasing. Well, look, the derivative of y with respect to t is negative degrees. See that? For change in t, your change in y is a negative change in y, right? Okay, and then Riddick asked the question, what about if, could x be cosine? All right, so let's hear blue version. X equals what? Or sorry, 4x equals cosine t. And x equals cosine t over 4. That would mean that y over 3 would be sine t. And y equals? Does it work? Have we done anything wrong? So what about this parametric function? Is it the same parametric function as this one? Are these the same function? But they give the same points. They give the same points. They'll give the same ellipse. But now this one's going to do what? This one's going to start at where? 1/4, 0 at t equals 0. And it's going to go which direction? This one will go counterclockwise. And you can, so how can we verify it's going counterclockwise? Look at the top. At the top, what's changing, x or y? X is changing at the top. What's the derivative? What's dx dt? Negative 1/4 sine t. At pi over 2, that value is negative 1/4. Does that show, if the dx dt is negative 1/4, does this show that the points are generated counterclockwise or clockwise? Because for a change in t, x decreases, negative. Again, negative first derivative means that's a decreasing quantity. That would indicate counterclockwise rotation. Because when you get to the top, you're heading left. You're heading left. And that's shown by the negative x derivative. Yeah. Do you follow? There's actually 8 different ways to choose cosine and sine. So once we're at this point right here, There's 8 different ways to choose either plus or minus cosine or plus or minus sine. And those 8 different ways are, we'll give you the 4 starting points, top, left, right, bottom, and then direction, right? So that makes 8 different possibilities. You could start here and go clockwise or counterclockwise. Likewise here, here, or here. And so by putting in, for this first step, plus or minus cosine, plus or minus sine, 8 possibilities of how to parameterize this curve. Each one gives a different starting point and direction, counterclockwise or clockwise. So that's our 4x and our 4x and our y over 3. So for instance, you can make 4x negative sine t and y over 3 positive cosine t. You can make 4x negative cosine t and y over 3 negative sine t. You've got all these combinations, and they're going to give you different starting points and an associated direction with it. Okay,